Hello everyone. Today I will discuss about the important question and answer of coordination compounds. Let's see. Our first question is write the IUPAC name of the following compounds. Now the first compound is a cationic complex. That means the cation is a complex. In this case we will first name the ligand. Now in this complex ammonia molecules are the ligand of this complex and cobalt is the central metal. In case of ammonia, according to IUPAC, amine name are used for ammonia. So there is 6 molecules of ammonia, so the name will be hexaamine. Now for the central metal we have to write the name of the metal, that is cobalt. The oxidation state of this cobalt is 3 and it is calculated as, let the oxidation state of cobalt is X plus oxidation state of ammonia, it is a neutral molecule, so the oxidation state will be 0. So there is 6 ammonia, so 6 into 0 plus the oxidation state of the chloride is -1, there is 3 chloride ions, so -1 into 3 equals to 0, so X equals to 3. So the oxidation state is 3. Now we have to write this oxidation state in Roman letter. So after the naming of this cation part, we have to write the name of the anion, and this is chloride, so it will be named as chloride. So it is our IUPAC name of this complex. Now for the naming of this ion, we have to write the name of the ligand first. Here the ligand is water and it is named as aqua, and the metal center is manganese. So the IUPAC name of this complex will be hexaaqua, because 6 water molecules are there, so hexaaqua. Then the name of the metal, that is manganese, and the oxidation state of manganese will be 2, because let the oxidation state of manganese is X plus oxidation state of water is 0, so 0 into 6 equals to the oxidation state of the complex is +2, so X equals to 2, so the oxidation state of manganese is 2, and here only the cation is present, so this will be named as ion. So the IUPAC name of this complex will be hexaaqua manganese 2 ion. Now for this complex there are 2 ligands, 2 types of ligand. First is amine and second is chloride. When chlorine atom is present as ligand in a complex, this is named as chloride. Now amine is started with letter A and chloride is started with letter C. So according to alphabetical order, the amine is named first. So here 2 ammonia molecules are present, so it is named as diamine. And there is 2 chloride ligand, so it is named as chlorido, dichlorido. After that we have to write the name of the metal center, and metal is platinum, so the name will be platinum. Platinum. Here the oxidation state of platinum is X plus 2 into 0 plus 2 into minus 1 plus 2 into minus 1 equals to 0. So X equals to 4. So the oxidation state of platinum is 4. Now we have to write the name of the anion, which is chloride. So this is the IUPAC name of this complex. It is diamine dichlorido platinum 4 chloride. For naming of this type of ion, here the ligand is a bidentate ligand. Bidentate ligand. That means these molecules, this is ethylene diamine, this is ethylene diamine. These molecules form two bonds, two coordinate bonds with the metal center. So for that type of molecules or ligand, we have to write the prefix is tris. For 3, we have to write tris for bidentate ligand. So here ethylene diamine is present, so the name will be ethylene diamine. Ethylene diamine. And it is present in a first diamine. So tris ethylene diamine. Now the name of the metal, that is cobalt. Cobalt. And now the oxidation state of cobalt, that is X plus 0 into 3 equals to 3. So X equals to 3. So the oxidation state of cobalt is 3. And this is an ion. So it will be end as ion. So the IUPAC name of this ion will be tris ethylene diamine cobalt 3 ion. Now for the IUPAC naming of that type of complex, which is basically an anionic complex. That means the anion is a complex. So we have to write the name of the cation first, that is potassium. So name started with potassium. After that we have to write the name of the complex. Here the ligand is cyanide. So it is named as cyanido. Cyanido. So 6 cyanido is present. So potassium hexacyanido. Hexacyanido. Now the metal is iron, and according to its Latin name, this will be written as ferrate. Metals when present in anionic complex, then it will be ended as ate. So the name of the complex is potassium hexacyanido ferrate, and the oxidation state of iron here, potassium is +1, so +1 into 3 plus iron is X and cyanide is -1, so -1 into 6 equals to 0, X equals to 3. So the oxidation state of iron is 3. So it is the IUPAC name of this complex, potassium hexacyanido ferrate 3. Now our next question is that type of complex naming. this complex is a neutral complex, and for this type of complex we have to write the name of the ligand first, and here 4 carbonyl ligands is present, so the name will be tetracarbonyl. Tetracarbonyl CO molecule, that is carbon monoxide, when present as ligand it is named as carbonyl. So this is carbonyl. So tetracarbonyl, and then the name of the metal, which is nickel. Tetracarbonyl nickel, and the oxidation state of nickel, that is X plus 0 into 4 equals to 0. So X equals to 0. So tetracarbonyl nickel and its oxidation state is 0. So the IUPAC name of this type of complex is tetracarbonyl nickel 0. Now, according to our next question, using Valence Bond Theory of bonding in complex, explain the geometry and magnetic nature of FeCN6 3- and FeH2 6 3+. So according to Valence Bond Theory, we have to write the electronic configuration of the central element first. So for this complex, we have to write the electronic configuration of the central element, that is iron. So the electronic configuration of the valence shell will be now the oxidation state of iron is 3. So iron is present as +3. So 3 electron is removed from 4s and 3d orbital. 4s 2 first, then 3d. So the electronic configuration of Fe3+ will be 4s 0, then 3d 5. Now the box diagram of Fe3+ will be 4s 0, 3d 5. This is 3d 5, and 4s 0. Then 4p is vacant, so 4p and 4d. Now the ligand is cyanide, which is a strong field ligand which can pair up this electron. So this will be jumped from here to this orbital, and this electron also be get promoted to the previous one. So after pairing, the configuration will be like that. First 2 will be paired up, and then 1 electron will be present as unpaired electron. Now there is hybridization will occur, and it requires 6 orbitals to donate the electron pair from cyanide to the metal center. Then these 2 orbitals, these orbitals and these 3 orbitals are participate in hybridization. So these 2 d orbitals, 1 s orbitals and 3 p orbitals participate in the hybridization, and after hybridization D2sp3 6 orbitals are formed. All these orbitals are D2sp3 hybridized. All these are D2sp3 hybridized. So cyanide can donate its electron pair to these orbitals of Fe3+. After donation, this is the electron pair of cyanide ion. So the hybridization of the central metal, that is hybridization of iron, will be D2sp3. The hybridization will be D2sp3. And after formation of this complex, one unpaired electron is present. So this complex will be paramagnetic in nature. When unpaired electron present in a complex, the complex will be paramagnetic. So due to the presence of this electron, the complex will be paramagnetic. The complex will be paramagnetic. And the shape of this molecule will be square bipyramidal or octahedral. This is an octahedral shaped molecule. So the geometry will be octahedral or square bipyramidal, and the magnetic nature is paramagnetic. Now our next compound is Fe-H2O6 3+, and after writing the electronic configuration we get this type of box diagram. Now water molecule is a weak field ligand, so it can't pair up this electron. So S 3p orbitals and 2d orbitals are participants in hybridization. So after formation of hybrid orbital we get 6 same type of hybrid orbital, and they are sp3d2 hybrid orbitals. So hybrid orbitals. Now water molecules can donate its lone pair of electron in these orbitals. These are the electron pair of water molecules. Now here 6 unpaired electrons are present in these molecules, this complex. So this complex will be paramagnetic in nature. Paramagnetic in nature. When in a complex there is no unpaired electron, the compound will be diamagnetic. Now the shape of the molecule will be square bipyramidal or octahedral shaped molecule. This is octahedral shaped. Octahedral or square bipyramidal shaped molecule. So the geometry of the molecule will be octahedral and the magnetic nature of the molecule will be paramagnetic. Now our next question is, draw the structures of geometrical isomers of this complex. Now the coordination number of cobalt is 6. So the shape of the molecule will be octahedral. Now there are two types of geometrical isomers will be present. Number 1, this molecule. This is trans isomer because 2 Cls are present in the opposite position and 2 chlorine atoms are present in the opposite direction. Now the cis isomer of this molecule will be like that. Now the two Cl atoms are present in the adjacent position, that is in 90-degree angle. Here the angle is 180 degree. So this is trans isomer, this is trans isomer, and this is cis isomer. This is trans form and this is cis form. So there are two molecules, two geometrical isomers of these molecules are as follows. Our next question is, name the types of isomerism by the following pairs of coordination compounds. Our first pair is this CONH3 whole 5 NO2Cl2 and CONH3 whole 5 ONOCl2. Here almost ligands are same, but the connection with the second ligand, that is NO2, it is connected with nitrogen atom, and here it is connected with oxygen atom. Here the NO2 molecule connected with N atom, and here it is connected with oxygen atom. So the connections are different. This type of ligands are called ambidentate ligand, and this type of isomerism is called linkage isomerism. Our next pair is CrH2 whole 5 Cl Cl2H2O and CrH2 whole 4 Cl2 Cl2H2O. Here the water molecules present as ligand, and here the number of water molecules present in the complex coordination sphere is 5, and here the number of water molecules present as ligand in the coordination sphere is 4. This type of isomers are called hydrated isomers. When the isomers are differ in the number of water molecules present as ligand in the molecule, this type of isomerisms are called hydrated isomerism. Now our next question is, this molecule gives a yellow PPT with AgNO3 solution, but the second compound doesn't. Why? Because the first compound, when ionized, it will form this cation and bromide as anion. So the solution of these molecules contains this ion, so it will react with AgNO3 solution and form precipitate of silver bromide. So for this case, a yellow PPT of AgBr will be visualized. But in case of the second compound, when it gets ionized, it will form this cation and sulfate as anion. As the bromine atom present as ligand with the central atom, so it can't be present in the solution, and that is why AgNO3 can't form with any PPT with this bromine ion. So the second compound can't form any PPT with AgNO3 solution. Our next question is, what are chelates, and give one example. Now chelates is a molecule or a complex where a ligand can form minimum 2 bond with the metal center. That means a metal is connected with a ligand with minimum 2 bond. here the ligand is a bidentate ligand, and form a close structure with the metal center. So this is a ligand. Now one example of ligand will be like that. Now the ethylene diamine molecule form two bonds with the copper ion. So this is a closed structure, and this compound will be, or this ion will be achieved. If this video is helpful to you, then like, comment, share and subscribe us. Thank you.